So this is me attempting, it's the first time I've tried to use this, but I write documents, not slides, right? I mean, I teach at Macquarie University. If I give slides, people say, can I have the slides afterwards? And I give them to them, and then they just come back to me with every question I gave them during the lecture, every word. So I've gotten in the habit of not writing slides, but instead writing notes. And then I don't want to go and write a separate set of slides. So instead I ask JavaScript to do some fancy stuff for me. Well, it's not that fancy, but JavaScript will, of course, come and kick me in the butt at some point, probably halfway through tonight's talk when it'll all stop working. But in the meantime, the way it is it's a document, and I'll just focus in on the bit that's interesting and what I'm talking about at the moment. And generally the bits in between are the things I'm saying, but they're typed down for two reasons. One, to force me to think about it properly before I get here, and secondly, so that the longer term record has some more details. I guess I started doing, so I went all over the shop with this. First I was doing slides that just had no information in them at all. They were just like pictures that were evocative of what was going on, and now I'm completely back the other way. So I'm an academic at Macquarie Uni. We teach Scala to our third year students. I've got around 50 of them at the moment. That means we pump out a fair number of good Scala programmers every year. This should be interesting to some of you. We also try and link up with industry through all kinds of programs that we have. So if you're all interested in intersecting with either our academics or our students, come and chat to me. We've got all kinds of opportunities. And we have some quite exceptionally good students, always. 3 or 4, I'd say, but that's, you only need one, right? So today I'm talking about pattern matching, and I just have been obsessed with pattern matching for a while, and I just can't let it go. So I'm back to talk about pattern, well, I'm not back, I've not talked about it here before, but I'm back talking about pattern matching again. So there are moments when you're studying, or at least there were for me, where you come across, in particular, algorithms, but just concepts or ideas that just kind of really just seem like magic. And unification was one of those, which got me interested in artificial intelligence for a short while. Then I came to my senses. And one of the things that brought me to my senses was the pattern compilation algorithm from Haskell. I mean, I'd been using these magic patterns. They did magic things for me, and all of a sudden I could understand how they did that. So that was 2001, 2002. And so since then, I've been so obsessed with pattern matching. And Scala, of course, has the greatest of all the pattern matches by far. It can do way more than any of the other languages. So since 2001 and since before, I've seen lots of extensions of pattern matching and ideas for pattern matching and other ways to do pattern matching, and all of them are subsumed by Scala's pattern matching. So the talk here is kind of how on earth that works. How do they get away with it, in a sense? Because there's no free lunches here. It's not like Haskell was written by a bunch of stooges who couldn't work out pattern matching, and only Odersky had the brains to make it work. No, there's trade-offs. All right, so we're starting off with something that should be obvious or might be obvious but might not be obvious and is really important in the pattern matching story, which is that a pattern match is really a switch. Now, the switch here that I'm talking about is a C kind of switch or a Java kind of switch. Unfortunately, the words get used a lot. Luckily, Scala used match instead of switch, which makes things a bit easier. So I'll use switch statement for C-style switches and match statements or case statements for what we see in Scala, and some combination of them for when I'm talking about functional languages. So these guys generally do the same thing, but we might like the left one better than the right one. Because it's more efficient, because all it does is inspect the value A, and it actually uses the value A to jump to the right part of the code. It doesn't even look at the bits that aren't the bits it needs. So if you give it a value 2, it doesn't even hit the first case. It goes straight down to the second one. Whereas with the if statement, it has to check each of the conditions in turn to work out which branch it's going to run. And this is at the heart of trying to understand Scala's pattern matching compilation, because all of the functional programming languages and everything else you've used that does pattern matching converts the complex patterns into a switch statement or a jump table. I'll refer to them one way or the other. So switch statements get compiled into jump tables. So I'll use the terms synonymously. So I guess the first question that got me started with Scala is how on earth is it compiling this stuff into switch statements? I mean, in effect, the answer is it's not, but I want to explain why it's not and what it does instead. But first I want to explain how Haskell and ML and other languages manage to convert pattern matches into switch statements, because it's not entirely obvious. Give me a little JavaScript. There we go. So I'm doing all this in Scala notation, even though what I'm showing you here is a Haskell algorithm. Now, the algorithms for the different functional languages are subtly different, but they all do compile down to jump tables in the end. So remembering that pattern matching in Scala is all about algebraic data types. You can, in fact, pattern match on anything, which we get to, but it's in the language because it's the way of pulling apart algebraic data as opposed to how we might pull apart object-oriented data via accesses. So we've got algebraic data up there. We've got an abstract class T, which is, I see sealed all the time these days, but I've never gotten in the habit of writing sealed myself. Although I assure you, when I tested all these, I tested them as sealed and abstract and made sure it didn't make a difference, because we'll get to potentially you think it might be able to make a difference. Then we've got the three different constructors for the type T, A, B, and C as case classes. A takes 2 arguments, B takes 1 argument, C takes no arguments. And so we have a match. Now, I've done this match on a tuple because it's impossible to understand pattern match compilation just on one scrutiny. Doesn't make any sense. The very first, your first pattern might be on one scrutiny, but it has to be expanded into a pattern on multiple scrutinies to get to the end result. So I always start with 2 just to get me going. So there's nothing special about this code. It just does some different things. So if the first argument we've got is an A containing a B, then we're on this. If it's an A containing a C, we're on one of these. If it's a B or a C, we're on these. And all of these are mutually exclusive. So this one requires the A to hold a B, which holds a C, and the second argument of the A is a 4. So a Haskell compiler would compile this. Oop, now I've lost. We're all just waiting for the JavaScript to screw me. Compiles into this. I may have made a mistake. I did this compilation in my head because I can't put Scala code into a Haskell compiler. You don't have to understand everything that's going on, but it's nested case statements. Switches on tags, and it jumps immediately to the spot it's supposed to be and ignores everything else. And there's lots and lots of nested switches and cases, and the E1, E2, E3, E4, and E5 is our actual code. And the trick to making this work is that we've got a tag for every constructor. So v1.tag is saying, do this switch, do this jump on whatever value you find in the tag of the thing you're inspecting. And I've used the notation v1 index 1, which isn't even valid Scala, to say the first argument of the v1 constructed value. So those things are easy in Haskell. Every constructor has, in fact, you can imagine constructors just as small integers. The first constructor, if we were doing a list, nil would be 1 or 0, depending on how we're indexing, and cons would be 2. And to get the first element in is a direct lookup because they've got control of the runtime, so they organize all of the things to sit in exactly the location where they want it. So we end up with switch jump, switch jump, switch jump, switch jump. In fact, you only have to do 3, I think, to get to the final answer, or maybe 1 more. And so getting through all of this is just a case of inspecting v1's tag and then jumping to another inspection. depending on where you are, then we might then inspect this spots tag, and that'll jump us to another location. And then in the end with this one, we have to choose between these two, so we inspect this guy's tag and jump to whichever of these is the correct one. Some things never even get looked at. It's obvious that things that are underscores don't get looked at, but even things that aren't... Oh, well, in this case, everything gets looked at. Now, the default is important here because this is not a complete pattern match. And so a pattern matching compiler, I think it's really neat to see what it does, is that it puts pattern match errors in all of these default sections. So if I was in Scala, this would be, I can't remember what the exact error is, match error and then a stack trace is what comes out at error. And you can just bung all those in, they're all the same everywhere. And they get put into exactly the right place. And down the bottom here, I haven't seen this in Scala, but I've seen it in Haskell. This is a piece of code that should never be reached because, in fact, I have case 1, case 2, and case 3, which covers A, B, and C, at the top level. There is no branch. I can't possibly miss out on that top branch. I'm guaranteed to match it. But then later on, there's plenty of places to miss out. So the default here is not an error. The default is one of these panics that you should never, ever get. So this also shows how relatively simple it is through this algorithm to do the kind of completeness checking you're going to want to do on a pattern match. The existence of these errors is the indication that you don't have complete coverage with your patterns. So that's the algorithm that Haskell uses, and ML uses that one as well, although probably one with some optimizations added as well. One of the places where optimizations can happen, if we just have a quick look, we can see the same value being inspected more than once. So V2 tag is inspected here and up there. V11 tag is inspected in 2 places as well. And so that's potentially a waste. And indeed, there was plenty of research. So if my memory serves me, I'll write it down here just to remind me. Mid to late 90s, people are doing the kind of compilation algorithm investigations, and they'd well and truly come up with the one that is still used in Haskell now by the time they'd done Haskell 98, in fact, a long time before. But there was still quite a lot of work afterwards on other types of patterns. How far can you push the patterns? And also, can you optimize this decision tree? And the results were fairly uninspiring. There were plenty of suggestions on how you can optimize them that theoretically were optimizations, but when tested in practice didn't make a big difference at all. And mostly that's because you can't come up with a really good heuristic to help direct your optimization of the decision tree. So I did put that code through Scala. And now this. So at first I am disappointed because there's no switch statements. There are ifs everywhere. And there's a lot of stuff that makes it really hard to understand. I'm not good enough at reading generated code. I can look at this and I can say, all right, there's some ifs in there. So it's obvious that, well, it's fairly obvious to me that this is compiling to nested if statements, not switch statements. And that's perhaps disappointing, especially once I put the sealed into my abstract class, because potentially I think to myself, that should be enough. I'm giving it exactly the same information that Haskell would have. Why can't I get it done? We'll talk about that. But I can't actually understand it well enough to convince myself. It's definitely compiling to ifs. And I've been burnt plenty of times by the further compilation and optimizations that happen through the JVM. And the Scala people are exceptionally good at doing these kinds of things. Every time I investigate something, they're doing something I never would have thought of. So I can't convince myself by looking at this that they aren't generating some if code that they know the JVM can optimize into something better. Yeah. So I've got to continue my investigation to try and work out what's going on. But, I mean, you've all probably done tutorials on Scala pattern matching, so you have an idea where we're going here. But hopefully I can flesh some of this out a bit. So certainly we understand pattern matching via these drop-down nested if semantics. When we're looking at a case statement, we're not thinking of it as if expressions, case expressions, switch expressions. We're thinking of it as a bunch of nested ifs. We're thinking that the first one's tried, and the second one's tried, and the third one's tried. We know that the bodies don't get executed unless they need to be. And that's useful. But it's really important to know whether they're all tried for at least one reason, which is that that's code. It might have side effects. We need to know if it's executed or not. So there's that. There's just wanting to understand things. But there's also hoping that Scala people have done something magic. And there's reading the Scala descriptions of the algorithm and not quite understanding how much magic's in there. So I got that a little bit out of order. Well, not out of order. Okay, so the tutorials will tell us that Scala does things via drop-down semantics, and this is getting some extensions from other programming languages for free by having this unapply approach. I mean, they're not for free because we're paying a price, and the price is that we're going to drop-down semantics instead of object-oriented semantics. So this is the first time where my little trick fails me because I didn't have a thing there. This is just some examples of actual extractor patterns that I've written. So they're sometimes called extractor objects. I generally use the unapply. But a companion object with an unapply method, we call them extractor object because it's extracting values. But by saying it's the unapply method, wherever you find it, it's just you find an object CC and call its unapply method, means you can jam them in anywhere, almost. So here I am defining on a case class. I've got an unapply. This is from a HTML web rendering experiment we're doing, and we want to do CSS selection using pattern matching in Scala. So we needed CSS selectors that go in pattern matching positions. So here's one that selects on the identifier. Is the identifier this string? It doesn't have to do much. It just looks up the place where the identifier will be held and finds out if it's none or some and returns exactly that value. But it's a nice notational convenience in that environment because without it, we'd have to write, where we would write ID cell and a string, we'd have to write sum, and we'd have to do a guard to get the props out of the ID out of the props, and it's nowhere near as nice. So it's also feeds into the DSL nature of Scala. It lets you write nice DSLs in the language because you now have control over what pattern matching does. You actually have complete control over what pattern matching does. Well, not complete. Only the very skeleton of the pattern match is defined for you. You fill in the unapplies that exist at every one of those branches, which means you have almost complete control over how it works. Control is good. Oops. So who's noticed a problem? There are always problems. No one yet. Oh, good. So I've been playing with pattern matching for quite a long time, and I've always been able to understand pattern matching in Scala just with this. I could tell anyone, I've left out an inverted comma at the start. Oh, that should be a full stop. I could say to someone, how does pattern matching work in Scala? And I could say patterns are converted to calls to unapply methods, and case classes are like normal classes that have an unapply method automatically created in their companion object. Does anybody disagree with that? I do. Does anyone else? Well, that's something... Yeah, so there's a couple of things. Exhaustive checking we haven't talked about yet. We haven't talked about sealed abstract classes as well. But there's something even more important than that. Those, I think. So I just got to use all my slide fanciness. It's not true. I think it's not true. I'm not sure it's not true. just as any time you're trying to delve into the internals of a language like Scala, things get a bit gnarly. The Scala spec actually says that case classes are not, they're described separately from extractor objects. There's a section for case classes that says how they work, the patterns work for a case class, and there's a section that says how extractor patterns work. And they kind of say the same thing, but they're separate. Why would they say that? So from my point of view, it's a red flag because in the languages from which Scala came, I didn't fix that link yet. In the languages from which Scala came, Pizza and Jacko, there were no extractor objects, but there were case classes. So Scala came from a fairly long experiment that involved Philip Wadler involved with pizza, but it's Odersky's, this is Odersky's drive since goodness knows when, is to bring functional programming to Java, and Scala was not the first attempt at that. Pizza and Jacko, at least along the way, had features that we end up seeing in Scala, so they're kind of like your, what do we call it, missing link in Neanderthals of the Scala world. And they both have case classes. And they have case classes to act as algebraic data types, and they have case classes with pattern matching. And they don't have extractor objects. Case classes in both those languages compile to switch statements using the Haskell algorithm. All right, now I'm very confused. Okay, yeah?
I came across something the other day that suggested, when you make a case class, there's also a flag that gets set on in the abstract data type, syntax tree, and that would result in different code generation when it came to it.
So I expect that case classes involve different code. In fact, I know of a few examples where they create different code, but I don't know the details, and I haven't found proper explanations of the details. So what follows next is a bit of an explanation from the outside, or exploration from the outside to try and understand. So now I'm quite confused, right? Everything I know about Scala on one hand tells me no, there's no compilation to switches, but everything I know about the antecedents of Scala tell me that, well, they did it perfectly well. So because I'm completely obsessed to this, I like the Haskell algorithm. I'd love to see anywhere that it's being used. I love what Scala does, and I want to see if there are ways that you can extend what the other languages do with the tricks from Scala. And I've got published accounts telling me that Pizza and Jacko can compile case classes using the Haskell ML algorithm. So let's try and get to the bottom of it. So I did a big empirical test. I've got lots of details here. I did it a few years ago. And the test is, if I've got a data type with 3,000 constructors in it, and I'm constantly working at the 3,000th constructor, if I'm working in jump tables, that gives me no penalty. If I'm working on drop-down semantics, the if statements, that's a penalty. So I created a benchmark program that does the same thing with ifs and with with integers and an algebraic data type representation of integers. And that means that on the real integers, I don't have the choice to use pattern matching. I do have the choice to use switches, but I'm in Haskell, so it's not a language feature. Rah, rah. I don't have a choice to use pattern matching. I can only define the algorithm using nested ifs, and I do that, and that's the blue dots. And as you go further down the numbers, further down your nested if, execution takes longer. Then I give the exact same algorithm, but instead of using actual integers, it uses an algebraic data type, which just has constructors for 1, 2, 3, 4, in this case down to 10, and run the same algorithm. And this time the algorithm can be defined with a case statement, and so you get no cost for jumping further down the algebraic data type. Nice. So you got a preview before. These are the results of doing the test properly 2 years ago on Scala. I've got the version in there. No, much older than that, 2.9. And in this case, the blue line is the ifs and the green line is the match statement. There is something strange going on with the ifs that I don't properly understand, but it does generally go up. But the case statements definitely go up. They're not flat. So I have empirical evidence and I can put in keywords left, right, and center, and I can't get that line flat. So I was convinced, all right, so even for case classes, in reality, Scala is compiling to nested if statements. I haven't been able to find a full explanation of how or what it actually does, whether it does go via extractor objects or whether it does something else internally, don't know. But I know it definitely doesn't go to jump tables. I reran it again just on Scala with a much smaller, much less repetition. So this is not a great test, but it was just to try and check if the results still held in the new version of Scala. And the results are even more inscrutable because the match version still goes up exactly as I'd expect, and the if actually still goes up, but at a very shallow angle. So something strange is going on, and I put this down to the same kinds of things that forced me to do this in the first case, which is there's so much going on between my Scala code and ultimately the JVM running. There's the Scala compiler, there's the bytecode compiler, there's the JIT bit that comes in and just optimizes away stuff that you do over and over again. But at least I know that the match statement still isn't trivially being compiled into a switch statement. So it's not too hard to work out why. These are the conditions that you need to use the Scala algorithm. You need the constructors of your algebraic data type to be fixed and known. And that you can get that by sealing your abstract class. That's a good start. So that's why sealing feels like something that will help. You need no repeated variables in patterns, and in fact Scala enforces that in its syntax as well, which is why it's bold there. But you need two other things. You need construction to be reversible, and you need constructor arity to be known and fixed for all constructors. And this is where Scala doesn't match those two. And exactly, so if you think about it this way, you think, okay, so that's why, even for case classes, it can't be done. Case classes as they are in Scala. And when I go back and look at Pizza and Jacko, the case classes are much more restricted. They don't have anywhere near the facilities for adding new methods. They don't have companion objects. I couldn't just write my own unapply method to add into them like I was able to before. So those languages are more restrictive. And so opening up what case classes can do in Scala has taken away the opportunity to compile down to switch statements. But, every other time I talk about this, which is only a couple of times, but some match statements in Scala do compile into jump tables. There is an annotation you can add to your switch, to your jump, that match. You can say that this should compile to a switch, and the compiler will give you an error if it isn't able to compile it to a match, to a jump table. All right, so then I do little experiments to find out what kinds of things actually can pass this test, and it's only, as far as I could tell when I checked 2 years ago, I'm going to rerun the tests on the new version of Scala, but it's only cases of literals, right? So very restrictive. Nothing to do with case classes in there. Not even non-literal constants. Even non-literal constants can cause trouble. Okay. So I'm not surprised that Scala can't convert to the benchmark code to jump tables, but it still leaves a big mystery that I now have to go solve. And this wasn't a mystery to me before I started preparing this talk, but it is now. What are case class pattern matches compiled to? So I think I'm off to do some source code digging, which might not be much fun. But if I find anything interesting, I'll promise I'll let you know. That's it. Any questions?
Questions. Okay. Jess.
Does this mean that in some, I'm going to say memory-constrained environments, despite the fact that I'm using Scala at this point, and maybe a memory-constrained environment isn't the exact place I'm in, but the fact that it doesn't compile down to a jump table in most cases means that I should be possibly aware of allocating shitloads of objects over time if I'm in a particularly hot switch statement or something.
I mean, yes and no. I think most Scala programmers are just thinking in the drop-down semantics anyway. It's unless you've for some reason got a habit of treating match statements, then you're unlikely to be accidentally doing things. You know how there's lots of things we accidentally do without realizing, but the back of our brain is paying attention to them. I think that's the kind of thing the back of your brain pays attention to. But certainly you've got to know that every one of those unapply methods, until the one is found, is executed. And like you say, if the unapply method is using lots of space, then even though that case isn't running, that memory is being used. Yep.
Just like to say that what a lot of those cases are doing is actually creating a partial function.
Yes.
And then doing partial function composition. And that's one of the reasons why you don't see JIT kick in for the latest one, is because it's partial function, you end up with a thing called megamorphic dispatch, which means that JIT can't do it because it just goes, oh, it's a partial function.
Right.
It's another partial function, another partial function. It can never actually implement those as direct, inline it, because it's not monomorphic or even polymorphic dispatch. Right. It's actually megamorphic. And that means that JIT is actually defeated in optimizing that case. Even though you've got a super hot loop, JIT can't do it.
So in Scala, we should now think of this exactly as a partial function instead of like a partial function?
It is actually a partial function, and it just does partial function composition. Yep. It says, if not this one, then the next one. If not that one, then the next one. Right. And it actually executes the guard twice.
Okay.
It has to execute the guard once to check it, and then it has to execute it second time as part of the actual function application, if it applies.
Okay.
Right. So there's an additional level of thing, which is a little bit annoying, but that's the question. When if you really want to optimize this stuff, you probably need to actually go away from actual pattern matching in a hot loop.
Another thing that I noticed, or I remember feeling when I was first reading about the way it actually works in Scala, is this is a lot of overhead. Like we're building 3 abstractions on top of each other to achieve something that we achieve with a compilation algorithm. Well, to achieve a superset of what we can achieve with a compilation algorithm. But it feels like it could get expensive fast, but then,
But 95% of your code isn't in your hot loop.
No,
right?
that's right.
That's the point, right?
Yeah.
Find out the 5% that is in your hot loop and then optimize that.
Yeah.
The
I
rest
guess it does
you don't
depend.
need to optimize.
I mean, we would suggest, especially when we're talking to people doing networking stuff, is that you want to do lots of stuff in this style. You might want to define actors or things that endpoints just in a partial function, in which case then you're well and truly deep into it. Oh, there was one other point I forgot to make, sorry, which is that kind of a corollary to not being able to find much performance benefit from the optimization of pattern compilation. I haven't been able to find much evidence that going to drop-down semantics is a problem either, because you just don't get the depth in your data types. So in a sense, I left that to the end because it forces this issue into intellectual curiosity, but I'm an academic, right?
But final observation is that in 2.12, when they move all of the function stuff into the Java 8 Lambda sort of infrastructure, potentially JIT can help in that situation, right? Because it moves into stuff which is now part of the low-level JVM machinery. Yep. So it's an open question whether it will or not, but it'd be interesting to see. Under 2.12, if you rerun your tests, see if it does help.
Yeah, something to do. I'll be. As I said, I now want to dive into this compiler source, which is a terrible thing to say. I'll follow
Especially
that. I'm going to write my own text editor, and I'm going to rewrite LaTeX because it's terrible. Just going to do all these things that you just constantly feel like doing. But right now, I feel like diving into compiler source, so I'm going to own it. Yep.
So in 2.11, Paul Phillips added this feature called name-based extractors. So instead of to reduce allocations when you're doing your unapply, so it doesn't make a new object, and in some cases you'll avoid 2 types of wrapping, I think. It'd be interesting to know whether the case class unapply is actually doing that.
Extractor,
so maybe.
Yep, absolutely. I should say that understanding these comes just from source code and published papers. And the published papers are all modern Scala. They're all from when there's not a lot of papers being published these days about this kind of stuff because Scala's moved from academic world to existence world. And the changes are probably a bit too quick for that as well.
It was full of bugs, if I remember correctly.
Well, yes. Yeah, but I don't think they were issues with the algorithms. The described algorithms that I find for the way Scala's compiled hold up quite well. It's just what I would call standard software engineering issues of any big system is where the problems were, yeah. Yeah.
Yeah, could you say anything about how the different algorithms affect how you can do exhaustiveness checking? And
yes.
that sort of...
So it's not so much the algorithms that affect exhaustiveness checking, it's the conditions under which the algorithms are working. And in the same... where did I put them? Further down here. So these are conditions. When you've got all these conditions, exhaustiveness checking is easy because exhaustiveness is just a case of checking that any generated switch statement includes every case. And if it doesn't, it's non-exhaustive. But when you're converting to nested ifs, for the same reason, if you're converting to nested ifs for the same reason that you can't enumerate all the cases, then you can't do exhaustiveness checking for sure. Sealed allows you to do the exhaustiveness checking, as far as I know. So this is the key point for exhaustiveness checking, is knowing which constructors can appear or knowing which subtypes of a type can appear. Yeah. Yep.
This is all sort of runtime stuff. Have you explored looking at the compiler to be a pattern matcher?
Yeah, so this is why I called it interpreting pattern matching, because we're understanding it, which is type of interpreting, but also the code is interpreted at runtime. I mean, if you think of what the difference between compilation and interpretation is, compilation makes a big transformation, and interpretation makes a smaller transformation. But in particular, we're still executing everything kind of step by step.
Yeah, so getting the compiler to create the dispatches in the code generation, not evaluating the dispatch at runtime.
I mean, I'm pretty sure that the Scala people have optimized the heck out of this. So Barak Amir, who's been responsible for this, both theoretically and practically in the early Scala things, has pushed it hard all the way. And that's one of the reasons that it's hard to understand what the algorithm does, because he's pushed it into every little nook and cranny and corner. Yeah.
Cool. I think come to the end.
You.
All right. Thanks very much, Matt. Let's have a...